Hi, my name is Jeremy Castagno. I live in Ann Arbor, Michigan with my wife and 3 kids. I'm currently pursuing my PhD in robotics at the University of Michigan. Previously, I did my bachelor's degree at Brigham Young University in chemical engineering with minors in computer science and mathematics. And I've actually received a master's degree in robotics as well from University of Michigan. This is my second time here at the NASA Langley Center, and I'm working here in the attractor group. So my overall goals for my research are to help assist UAVs with good decision making when they're over cities, to help them make decisions about where they need to land when there's an emergency, such as when there's low battery or bad weather, or maybe if there's a life flight coming through, to help it make choices. And a lot of that includes making maps about the area and also helping it make real-time decisions about where to land. What I'm currently working on here at NASA Langley is actually working on real-time rooftop landing, where it uses the LiDAR information to create a depth information about the environment and helps it to avoid obstacles that are on the rooftop and then to land on it. So how it basically works from beginning to end is that we can take this LiDAR information and we can take our information from our flight controller that gives us our orientation and our positions. We can take the point cloud that's generated from the LiDAR. We can rotate and translate it using the information we have from the flight controller, and then we can generate a point cloud that's over on top of a rooftop. And then we can take those point clouds and create meshes of the environment, and then we can look at those meshes and analyze them and find areas that are flat, and we can extract that information from it. And at the same time, we can find areas that are not flat, like or obstacle-like, and we can remove them. We can make holes inside those meshes. And then finally, we can take this mesh, which is just a list of triangles, and we can very quickly and rapidly turn that into a polygon that expresses the landing site area, and there will be holes inside that polygon as well. So we can have a very succinct, very small representation of our landing area. And then after that's done, then we can use an optimization algorithm that can very quickly find the largest inscribed circle that's within that polygon, which is guaranteed to be flat, and that's farthest away from any obstacles, which are the holes in the meshes. So there are a lot of examples for what I just talked about for the point cloud extraction of the mesh. We can use it for rooftop landing, like I'm using it for, like I developed for, but you can also use it for pothole detection. If you were putting this on the car and you developed a point cloud of the ground, you can find and determine where potholes are and get their shapes and so forth. You can do it for drivable surfaces for autonomous navigation to help you know when there's obstacles that are in front of you. This very specific part that I'm testing out this summer, it's really about once you arrive at a rooftop and you're there and you have information a priori or before that says it's a good rooftop, it's a way to verify that it's true, to verify that this rooftop truly is going to be safe to land on, and it will help you inform a decision about where to land. So the entire goal of my research is to kind of assimilate 2 types of pieces of information. Information that we've collected and we know before. That information such as like satellite images of cities, so we know where all the buildings are, we know the roof shapes from that. We have information about map data from those cities. We have information from GIS scientists that tell us what the point clouds of those cities have already been collected. And so I can use all of that information, process it, and have that available for the UAS before it even takes off. And then we should use all of our local sensors that we have available as well, and kind of fuse those pieces of information together. And so that can give a UAS really the ability to make very good decisions about where it should go, where it should land. And so my research is all about kind of using both of those information, the real-time information and also any information that's been collected previously.